It's such a pleasure to be here, and I want to thank Francesco for inviting me to this beautiful, beautiful place. Not only is this a beautiful place, but the people are beautiful, and the talks have been so interesting, and I'm so impressed. I am the president of ISIS, and I'm so impressed by the Italian fracture group, and that it makes such a contribution, an important contribution to ISIS. So I want to thank all of you and thank Francesco especially for this. I'm going to talk to you about work, and I was mentioning to Francesco that actually started in, I think I said 1991, something like 1991. The whole idea of this started, it started not with composite materials, it started with interface fracture and developed over many years. And so you see my name appear by itself on the talk, but actually if I were to put all the people that made contributions, you would see many. I have 2 engineers that work in my lab, and I used to have a technician. There was a postdoc, and then many, many students, PhD and MSc students. Our MSc is a very serious degree. The students write a thesis, and so they do carry out research. And 2 of the people on this list, Orly and Lucy, are now doing PhDs. So it's been a very interesting period. Okay, so today we're going to speak about composites, and so to give you a little introduction into composites, we can look at the Eurobus series of airplanes, and we can see that beginning in the early 70s, about 5% of the airplane was made by weight was made of composites. And today, when you fly in their newest airplane, the A350, we're now over 50%. And I might say that I worry a bit because there's so much unknown about composites, and yet we're flying in these airplanes. Not to forget about Boeing. In many of their planes, and in particular in the Dreamliner and the 787, they also have 50% by weight of composites. So we're stuck with composites, and we need to learn as much as we can about them. And so we're going to talk about some of the problems in composites. First of all, let me talk about and explain what a laminate is. We've heard talks about steel and aluminum, and so maybe there are people here who don't know a lot about composites, and that's fine. So let me just try to explain it right from the beginning. A composite material is composed of more than one component, one constituent. So you can take a matrix, which is epoxy, and you can put in particles of different kinds of material. Now here we're going to talk about laminates, and we're going to talk about what's called multi-directional laminates, but each ply is unidirectional. So what you see here is you see a layup of a laminate. There are many different layers or plies, and each ply here we're thinking of has fibers, long fibers, in a certain direction. So if I look at this ply, I can say perhaps that all the fibers are in this direction, in the y direction, in the 0 degree direction, along the axial direction. And the next ply can, for example, have plies coming out of the screen. And so they're in the 90 degree direction when they're coming out. And then we can put fibers so they're in the 45 degree direction and the minus 45. And we compose a layup and we obtain a laminate. And then typically what happens is we have different failure modes. And the 2 most prevalent failure modes in laminate composites are matrix cracking. That is, the fibers here, let's say, are not in the 0 degree direction, because that would be very strong, and we get cracking through the matrix, through the epoxy, for example. Or another mode of failure, and that's what we're going to speak about, is delamination. We get a separation between the various layers, and that's a very prevalent mode of failure. It's a fundamental mode of failure, and the common sources are material and structural discontinuities, in-service loads, and in particular impact. A plane is flying along, moving along the ground, and a stone hits the wing, and it impacts it, and it causes separation of the layers. It's very common, unfortunately. And so the delaminations tend to occur between plies of different orientations. So what the airplane companies do, because they don't use damage tolerances they do for metals, they use over-design, they use very high safety factors, and so that they won't obtain failure. But this is a waste. It's a waste of material. It's a waste of weight. It's not fuel efficient. And so what we need is we need to give them accurate fracture toughness values so that we can bring down this over-design. And one thing I haven't said here, which I won't talk about, is we also need to understand the fatigue properties of these materials. But I'm only going to talk today about fracture toughness. So to begin with, we'll talk about interface fracture. And you'll notice anisotropic materials, and some of you may be scratching your head, why is she speaking about anisotropic materials? Composite materials are anisotropic and inhomogeneous. But what we can do, and what is typically done, is we use some sort of a homogenization procedure or micromechanical procedure, and we homogenize the material, and we look at it as if it's homogeneous, but anisotropic. So if we think about the ply, which has fibers in the 0 degree direction, it has a high Young's modulus in the direction of the fibers and a very low Young's modulus perpendicular to it. So it's anisotropic. And we're going to consider one interface. We've done more than this, but because of time limitations, we'll look at what's called the 0-90 interface, and I will explain that. And we carried out tests on Brazilian disc specimens. So we will look at these tests. And then we need a failure curve. So we obtain a deterministic failure curve, and because of the scatter, we felt that it would be important to go on and do something statistical, and we will talk about that today. And then we'll come to some conclusions. So here is the Brazilian disc specimen. Here is one example of it. It's about 40 millimeters in diameter, and this particular one has fibers in the 0 degree direction, fibers coming out at you in the 90 degree direction, and fibers in the 0 degree direction. The composite strip is about 12 millimeters in width. And this is another layer. Here we have, again, 0, 90, 0. And we have stiffening composite layers so that the plate that was made wouldn't bend. And when we carry out the analyses, we model it all. And we place these aluminum discs to get a circular specimen, because for handling, if we only tried to load this composite strip, we would have a lot of difficulty. Okay, the load is going through the center of the delamination. Here is the delamination. And by rotating the specimen, we get a full host of mixed modes. So again, to explain the 0 and 90, the x1 direction is along this layer, and as I'm showing you. And so here in the 0 degree, the fiber's along x1, x3 is coming out at you, and x2 is perpendicular to the delamination. And in this layer, we have fibers in the 90 degree direction, so they're coming out at us in the x3 direction. So we carried out tests on this type of specimen and this type of specimen. And I must say that when we had to carry out tests in this type of specimen, I said to myself, I'm very worried, because if we didn't really measure a fracture property, we would expect that we might get different results between this specimen and this specimen. And that was, I stayed up a few nights worrying about that, but it all worked out in the end. It worked out. All right, for those of you who are not mathematically oriented, you can dream a little bit. I think we could even manage. I'm not sure we can manage without these slides but I think it's important to discuss this. I'm sure that everybody here knows that if I have homogeneous material, the stresses behave as 1 over the square root of the distance from the crack tip. Okay, now we have 2 materials, and we have 2 anisotropic materials. So we have, first of all, we're looking at the in-plane stresses. Alpha and beta is 1 and 2. And we have different functions. These functions are different if we have material that's in the upper half space or material in the lower half space, 1, 1, and 2. Now here is our 1 over the square root of r. 1 over the square root of r singularity. And then we have this other r to the I epsilon, which when people look at it, they say, oh my God, and then they close their minds. Don't close your minds. All this does, the I is square root of -1, and epsilon is a very small parameter that depends on the mechanical properties of the material. And so what it does is, as the stresses are going to up to infinity, 1 over the square root of r, they start to oscillate very rapidly. And as long as that's relegated to a very small zone, we can use these ideas. One has to examine that, and as long as that occurs, we're okay. Okay, now K, we're used to K1 Roman and K2 Roman, and here we have this K1 and K2. This is for interface cracks, this is the mode 1 and the mode 2 stress intensity factors, which are combined into a complex stress intensity factor. And so if we look at the units of K, this, by the way, is the real part of this. This is the imaginary part of this. So everything is real, the stresses are real, not to worry. And so if we look at the units, this is force to length squared. And so we have a length to the 1/2. So this entire thing is force lengths to the 3/2, but then K has an R to a length to the -I epsilon, which makes them crazy units. And if you change the units from millimeters to meters or vice versa, you don't have a relation between K1 and K2 as you would have in the ordinary homogeneous isotropic material. But not to worry, because you can keep track of it. It's just mathematics, and one can get a handle on it. Now, these functions, which are nice functions, they're bounded functions of theta. We have one for mode 1, one for mode 2. They have to do with whether we're talking about sigma 1,1 or sigma 1,2. And it depends whether upper or lower. And we have analytic expressions for these. They're not numerical. And we get them from the stroke formalism. And as I said, epsilon, I didn't call it, but epsilon is called the oscillatory parameter. It's causing the stresses to oscillate. And then we can do the same thing for the out-of-plane. And it turns out for 090, the out-of-plane behavior is the usual 1 over square root of r. We have K3, the mode 3 stress intensity factor, and we obtain this expression again from the stroke formalism. So we have an analytic expression for the first term of the asymptotic solution in the neighborhood of the delamination front. And so because K has such problematic units, one does something to normalize them and multiplies by a length scale to the I epsilon, and this K hat has normal stress intensity factor units, force, length to the 3/2. And the question is how to choose L hat, and that comes out of the experiments. So in addition, we can define two phase angles. This is basically K2 to K1. This is K2 hat to K1 hat, so it's a mode mixity. And actually for our 090, we're not going to look at this other phase angle, which is a relation between mode 3 and the in-plane modes. And these functions, H1 and H2, are Young's modulus type quantities. There's somebody who is familiar with the stress intensity, with the relation between G, the energy release rate, and K. You have 1 over E or 1 over E bar generally in homogeneous materials. So here we have this H1 and H2, and these, both epsilon and these D quantities depend on mechanical properties. So you can think of H1 as being Young's modulus, if it makes it simpler. And then we have an expression for the energy, the interface energy release rate. And so it's very similar for homogeneous materials. And so now we needed to analyze our test specimens. We carried out a test, we obtained the applied load, we know the geometry, we know the crack length, the delamination length when it fractures. And so we used finite elements and a conservative M integral, and we only did this in 2 dimensions, and we examined the implications of that, and it's okay. And so we obtained K1 for applied load for force and K2 for force. One mustn't forget that when you have composite materials, you're curing them. These were cured at 177 degrees Celsius. So you also have residual stresses, and we obtained K1 and K2 for residual stresses, also from an M integral. So now we take our Ks, and we have linear elasticity. We don't have plasticity in this case. It's very, very small. These materials are brittle. We superpose the K1s from applied load and from residual stresses. The K2 is superposed. We then obtain G from the K totals, and this is basically K2 hat divided by K1 hat. And here are our specimens. As I said, they're 40 millimeters, and you can see the relative sizes, 4 millimeters each, and here they're 0.5 millimeter each, plus the stiffening layers. The material used was AS4, which is a carbon fiber in 3502 epoxy matrix, and we had a volume fraction of 62% of fibers. And here is our loading frame. So as we rotate the specimen and we load in this direction, we get a whole host of mixed modes. So it's a very convenient specimen. And here is our experimental setup. You see our instrument machine. The specimen, I don't think you can see, is in there. The upper grid is not touching yet the specimen. And we do everything with a video microscope so that we can look, afterwards we can look at the films again and again and see what's happening. Okay, what's left? What's left is to do the tests and to have a failure criterion. So you can take the expression for G, which is, thank you. Thank you. You can take the expression for G and you can rewrite it in terms of these hat quantities. You have to know mathematically why it just comes out to, you're just putting the hat quantities on it. It's trivial if you do it. And recall that K hat is a normalized K, so it has the normal units of stress intensity factor. H is just a function of mechanical properties. And you can manipulate this expression so that you write it in this way. So this is the failure criterion. You manipulate this, and what I'll explain what psi is, I'll remind you what psi is, and what G1C is. We carry out, let's say, 25 different experiments, and we analyze them, and we obtain a value for K1 hat. We square it, we divide by H1, and then we take the average for all of them. So this is an average G1C value, and psi is just the mode mixity, K2 hat to K1 hat, the arctan. So this is our failure criterion, and here is a graph of the failure criterion. Here is the failure curve, and let me explain to you what it means. Suppose I have the same interface in a structure and it's a complicated structure, and I make an assumption of the kind of delamination I have, and I say, okay, let me calculate K1 and K2. I calculate K1 and K2, and I find a value of psi, and I'm along the psi axis. You will recall that psi actually depends on L, and what L does is it translates this psi axis. So you calculate your psi for the L that you use to obtain this curve. You calculate your GI, and if you're above here, that means that you're going to expect failure. And if you're below when you calculate it, that means that you're in a safe zone. So all values below this curve are safe, and all values above this curve indicate failure. And if, let's say, you do something like this for a plane that an airplane that you're designing, you say, I'm going to have failure, so I better redesign, I better make the part thicker, I better change the geometry in this place in order to be below the curve. What is the problem with this? The problem with this is statistically, we have points below the curve which fractured in our tests. We have test points below the curve where it should be safe. And that drove us to do a statistical analysis. So to say that I'll give you a new curve, which will be more conservative, it'll be lower, but then I'll only have a certain percentage of probability of failure in that safe zone. So that's what we did. And so we used a standard normal distribution. And this is the probability density, this axis. And you can calculate the probability P to a certain standard normal variant, ZP. So if I choose ZP to be this number, then I'm talking about a probability failure of 10%. That is, any point that's in this region has a 10% probability that there'll be unexpected failure in what we call the safe zone. So we can use these ideas in order to lower our G1C average quantity. We have the number of samples are n. The standard deviation of G1C bar is S. We calculate this K factor, which depends on ZP and Z gamma. You can see ZP and Z gamma. And so P is the probability, and we chose a confidence of 95%. So we have 10% probability of failure in the safe zone, 95% confidence in our choice of that curve. And so we now have a new curve in which we've lowered the G1C value to G1C star, and we plot this curve. And so we can see it here. This is the deterministic curve. And this is the statistical curve where we've lowered the G1C value as we've done here. Okay, and so then this would say, if we chose 10%, there was only a 10% probability that we have a failure in the safe zone with a 95% confidence interval. Okay, so we're considering the 0-90 interface, and you will recall the oscillating parameter epsilon, which is very, very small. We had 24 tests. We calculated G1C bar to be 26.2 newtons per meter. The standard deviation is 11.5, which is rather high. And so with this K value that comes out of the statistics, we have a new value, G1C star, which is much lower. But now we only have a 10% possibility of failure in the safe zone. So here are the test points in blue from these two specimens. And from this specimen, the test points were over here, and they lied in the scatter of the other specimens. And you can see the scatter. These are supposed to be safe points, and they're not safe points because you have to always have statistical error when you're carrying out tests. And so this is the failure curve, and you choose L to center the data about 0. That's the first choice of L. And then you choose L if you refine it in order to get the best fit that you can between the data and the failure curve. And let me just say that looking at this curve, we have a lot of confidence in it. And the reason we have confidence is these points, which are far out, and this is far out in mode 2, agree very well with the curve. They're not, it's not like this point is not that good, but it certainly isn't over here. It's near the curve. And this was our G1C bar, which was 26.2. And then for our new failure curve, which we have a 10% probability of failure below it, this is this curve, in which G1C star is 5.1 newtons per meter. And so we will conclude that we have looked at the interface fraction mechanics principles for anisotropic material. We carried out tests on resilient disc specimen. We did it for the 0-90 interface, and that's what I presented to you. We also did it for the plus 45, minus 45 degree interface, and this is a stronger, it turns out to be a stronger interface. The G1C value is about 90 newtons per meter. All specimens were analyzed by means of the finite element method, which I didn't present to you, and conservative M integrals, which I also didn't present, I just mentioned them. And we obtained 2 failure curves. One is a deterministic failure curve, and the other one has a 10% probability of unexpected failure. We could do it with any percentage that a company, let's say an airplane company, would like, with a 95% confidence. And now we're working on different layups. We're working on woven composites. We've done DCB specimen testing using woven composites. Someone showed us, I think, DCB testing here yesterday, and so we're getting G1C values. We're also carrying out fatigue delamination propagation tests. We've done this also with some woven composites with DCB, and we're going to be starting to work on mode 2 and mixed mode in these directions, because you need a complete picture not only of the fracture toughness, you also need the fatigue parameters in order to do some sort of a damage tolerance paradigm for, let's say, for an airplane. Okay, thank you very much.